to start by drawing a little picture of what's happening. 16 minus x squared is the same as minus x squared plus 16. And you see that that's a parabola shifted up 16 units. That's opening down. Technically, the x-intercept of this would easily be minus 4 and positive 4. Agreed? So we have a picture. What are we trying to find? We are trying to find this area. I love using crayons for area. Feel like orange today. This is the area we're trying to find. You have no formulas for parts of parabola, right? Have you ever had on a formula sheet part of parabola formula area? No. So this is actually going to be useful. As opposed to the last question where you could definitely see it was a triangle, we could find the answer in less than 5 seconds, and we chose to do it in over 10 minutes. Inherently, there should be a problem in that, right? But this one we have no formula, so now we have this idea of, can I break this up into a bunch of different rectangles? And this time I'm going to find my lower sums. So would you agree that from 0 to 4, this distance is 4? And if we divide it into n equal sections, then one of these sections, where I draw a rectangle, one of those sections, that length on the bottom would be 4 over n. And here I've got a number line, and I went from 0 to 4, and I broke it up into little sections. Each of these little sections is 4 over n. So does it make sense that if this is a change of x is 4 over n, then this first point, x1, would be at 4 over n. And x2 would be 2 of those. It would be at 8 over n. And the ith one would just be I times 4 over n. And now that we've seen the second one, hopefully this is starting to be like, oh, this makes more, I see it better. Each of our rectangles are going to be, right, when you plug in 4i over n into f of x, well, f of x was 16 minus x squared. So we have to plug in the 4i over n in for the x, and we get 16 minus 4i over n squared. That's going to be the height of every single rectangle. And we have to add up all of those rectangles. So the algebra says this is the height of every single rectangle as I goes from 1 to n. This is the width of every single rectangle. They're always 4 over n. And we have to find this sum. So our goal next is to get this equation into formulas that you know. Okay? And the formulas that we were given at the beginning were I equals 1 to n of I equals 1 to n of I squared. I think I gave you 3 of them. I equals 1 to n of I cubed. We are also going to do a new one today that I think you'll figure out quite easily. Don't even have to give you a formula. So these formulas I gave you previously. We need to rearrange this, clean up things, use properties of sums to get it to look like those. So what can we do? Well, I could distribute this 4 over n. That'll give me 64 over n. And if I square the 4 to get 16 and multiply by another 4, I'll get negative 64 I squared over n cubed. At this moment, I'm thinking this one. I see an I squared. We also have to realize that before we send n to infinity, we're imagining n could be any number. So it is a constant. Could be 7, could be 1,000. It's a number. So anytime that we have numbers, we can pull them out in front of the sum because they're a constant. So a little bit of algebra I can do. I can pull out a 64 over n out of this one. I can break these sums up separately, and I can pull out the 64 n cubed out of the second one. So properties of sums, you can do the sum of each adding and subtracting separately. So I did that, and then anything that's a constant can be pulled out in front. So I pulled out the 64 over n, and I pulled out the 64 over n cubed. And now for sure, look at this. I have got that part by itself. And that was a formula that you'd have to look back in your notes exactly, because none of you have it memorized yet. That's okay. You won't really have to memorize it, I don't think you'll ever. Because once you do the exam, you're going to learn, I'll even show you at the end of this. I'm probably not supposed to yet, but I'll show you the shortcut. Yeah.
I might be kind of fuzzy on the rules of the sum stuff, but if you take out 64 over n,
yeah,
and it's times the whole thing, don't you also have to take it away from 64i squared over n cubed?
So technically what I did here first, sort of imagine this. Imagine I had this sum I equals 1 to n of the 64 over n minus, and then I did this sum I equals 1 to n of 64i squared over n cubed. Because the sum of two different adding and subtracting, you can do the sum of each of them separately.
Oh, yeah.
And then I didn't factor this, I know what you're thinking, did you factor the 64 out of n out of both of them? No, I just thought of it separate like this, and just took the 64 n out of this one, and then I took the 64 over n cubed out of that one. Does that make sense?
Yeah, it does.
Okay. I know what you're thinking. You're thinking, oh, did you factor it out of all of them? But there's not brackets here. This doesn't distribute to that. Okay, perfect. So in the green box, you'd have to look back. Can you quickly tell me what the answer is to this sum? What is I equals 1 to n of 1? It's not just 1. Okay? So, what does it, yeah, it's n. What does it mean? It means start when I is 1. Wherever there's an I, there is no I. Plug in 1. So you would have nowhere to plug in the 1. What would be left is just 1. Then you do 2. You plug in 2, there's nowhere to plug in 2. What's left is 1. So now you have 1 plus 1. And then you do it for 3, and you'd have 1 plus 1 plus 1. You do this n times. If you do 1 plus 1 plus 1 plus 1 plus 1 n times, what will you get? Yeah, I did it 5 times. I got, I'll try 10. I got 10. Does it make sense that if you add this up n times, you will get n? Okay? But this is a great example of, if you were just looking online at a solution, you'd be like, what the heck? How did they go from here, circle it in orange, how did they go from there to there? Sometimes we have to break things down and think about them a little bit, and it's like, oh, it's super easy once you see it. But if you were just looking online at notes, you'd probably get confused at that point. And then this, I'll put it in green, that's the formula for adding up squares, which you probably didn't remember, but it's in your notes. And if you didn't memorize it, you're probably going to be just fine. But it is n times n plus 1 times 2n plus 1, all divided by 6. It's kind of a pretty formula. Okay, so this is simplified the sum of all those rectangles. If you plugged in a 3, it'd be like you made 3 rectangles, what its area would be. If you plugged in 7, it's like you made 7 rectangles, what its area. We just created a formula for any amount of rectangles. Instead of doing a specific one, we've got the formula for all of them. Then if we take this and simplify it, well, the n and the n cancel out to be just 64. I multiplied out this on the top, and I did 64 over 6, simplified that to 32 over 3. And can you see that I could distribute that? If I distributed it, I'd get 64 minus 64 over 3 minus 32 over n minus 32 over n squared. Now that is the formula simplified. If you wanted to put only one rectangle, you plug in 1 for n, and you would find out, here, let's draw, feel like drawing that rectangle. Oh yeah, that's a really fun rectangle. If it's a lower sum and you only do one rectangle, it would be flat. It would be 0. If I plug in 1, do I get 0? This is 32, 32. Oh, I actually get a negative? Ooh, yes.
Is it because you multiplied the, the 3 binomials at the top? Because you should get an n cube, if I'm not mistaken.
Oh, I canceled out one of these n's with this n.
Oh.
That got me the n squared. Okay. Anyway, so we have, this is our simplified formula. If we take the limit as n goes to infinity, that should be the area. Do you see how nicely these just disappear? If you go n to infinity, those just become 0. And we end up with that shaded orange part is 128 over 3. Crazy. Yes.
Where are the formulas for
The sums, they're in your notes. So we had them in the summation part, in your notes. Go back to where the sum stuff was. There they are.
Oh.
They have K instead of I. Right? In your notes, they have K equals 1 and have K squared instead of I equals 1 and have I squared. Which can throw you off completely until you realize, oh, they just changed the limit. Not too crazy. Now, you're not supposed to know this yet. And technically, you won't be allowed to use it until we've fully proven it. But if I take the integral of 16 minus x squared dx from 0 to 4, the integral would be really easy, 16x plus x cubed over 3. And since I showed you this the other day from 0 to 4, this would be 0 to 4, which means you should plug in 4, and 4 would give me 64 minus plus 64 over 3. And subtract and plug in 0, which is 0 plus 0. We get 64 plus 64. Oh, sorry. I made a tiny mistake. This is a minus sign. Do you see that tiny mistake? You ever do mistakes like this where you miraculously change positive signs to minus signs? So technically those should be minus and minus. And we get 65 minus 64 over 3 in under 20 seconds. But I think most of you will prefer the 10-minute method in the end. Be like, right? It's like reading a book and watching a movie. The book is always better. So you'd much rather do the much longer process than the very short, easy way. But we have to develop this in order to explain why the shortcut works. Okay? So these were lower sums and upper sums. But then people said, oh, you know what's the problem with lower sums and upper sums? What happens if, I wanted to find this area? Sometimes my lower sum is the left side. Sometimes my lower sum is the right side. But sometimes my lower sum, like if this was my rectangle, oh my goodness, my lower sum's actually in the middle. It's a problem.
You should do both and take the average.
Could do both, but the limit as you do them all is the same. So we get to a famous mathematician who was exploring this. Can anybody guess what his last name was? Riemann, right? I'm desperately trying to find something very good in mathematics that they can, polish the JR blah 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 for the rest of humanity forever and ever, but that hasn't happened. Try slowly. Yeah. Reality's probably not. It's not going to happen. I'm still hopeful. Okay. So Riemann. What did Riemann do? He said, well, if the area is equal to the limit of the lower sums and it's equal to the limit of the upper sums, but sometimes we have these graphs that it's not easy to do just lower and it's not easy to do just upper. Does it really matter? No. Here's the idea. Okay. First of all of the graphs that we've done so far have made the following assumptions. Okay. Your graph has to be continuous. If it's broken, it's very hard to do rectangles underneath parts that are broken. If there's asymptotes that go up forever, we've got issues with areas under those curves. So first of all, we want to make sure our function that we're thinking about is continuous. We're going to start with it being non-negative, so just like this graph, it's all above. Okay? We'll get to negative stuffs in a bit, and it'll be fun and interesting. Our change of x is separated into sub-intervals. So whatever, we did this exactly the same. Whatever the distance from A to B is, you divide it into n equal sections. And we still have our absolute minimum and our absolute maximum on each interval. We already know, that if we did all the lower ones and we did the limit as n goes to infinity, and we did all the upper ones and we did the limit as n goes to infinity, that both go to the area. Okay? So we already know that. But now we're picking some arbitrary number of a new height. And that new height is obviously bigger than the minimum, but smaller than the maximum in that space. Right? So if I think about this rectangle that I've drawn, this green rectangle is definitely the minimum. This blue rectangle here would be the maximum. And any other point I pick in there, if I pick this point there and made the rectangle, it would be in between. Right? Initially, mathematicians didn't like this because they liked the idea of saying, well, if I choose an area that's below, I for sure get an underestimate. If I choose an area above, I for sure get an overestimate. And if I go to infinity and my overestimate and underestimate come to the same thing, then that must be the area. If you take a value in the middle, it's like, ooh, sometimes it's an overestimate, sometimes it's an underestimate. This makes us feel a little bit uncomfortable. But if we think about what's happening, okay? I don't know about the letter U. I feel somewhat awkward teaching you and saying F you a bunch of times, so just I apologize ahead of time. I also don't like the word that comes to mind when I look at all those letters, but that's okay. All right. So we know that FU is in between the little c and the big C. It's somewhere in there. And if we added up all the little sums and we added up all the big sums, the FU sums would be somewhere in the middle. That's for sure. So we know that the sum of the one in the middle has to be somewhere in between the lower sum and the upper sum. It could be equal. Maybe you always choose the biggest ones. Or it could be equal to always the smallest one. So it's somewhere directly in between. But since we know the limit as n goes to infinity of this one is the area, and the limit of this one is the area, by the squeeze theorem, the middle one has to be the area. This was really freeing to mathematicians because now you didn't have to worry about, did I always get the lower ones? Or did I always get the upper ones? Just like, I'm just going to pick random ones. And later mathematician says, yeah, and if you want to pick some wider and some narrower, that actually doesn't matter. As long as you do it to infinity, they'll all get small to 0 anyways. And so we have this new idea, which are called Riemann sums. It doesn't matter if you pick the biggest or the smallest all the time. You just have to pick anything. And if you make the limit go to infinity, it's going to be approaching that area. So, it's defined. It's continuous. Okay? We find out that it doesn't necessarily have to be continuous, which is interesting. Okay? It doesn't necessarily have to be non-negative. We're going to find out that areas that are below the x-axis are actually negative areas, and areas above are positive areas. The widths don't have to be the same length. So he sort of broke down all the common things that we started with, and he proved that you can make this work with a bunch of different functions and not necessarily have all of the things that we started with exactly the same. Right? And you can take any value in a subinterval. So as a result, we come up with things called left Riemann sums, right Riemann sums. There's also midpoint Riemann sums, but more commonly we do left and right. It's like instead of always finding the smallest one, why don't we always use the left point? Instead of always finding the biggest one, why don't we always use a right point? And this frees us up to do functions that aren't necessarily always increasing or always decreasing. So here's the function x squared minus 3. The graph is shown. We're going from 0 to 6, and our subintervals are not necessarily the same length. We've got one that's 0 to 1, one that's 1 to 2, one that's 2 to 4, and one that's 4 to 6. So sometimes the width is 1, and sometimes the width is 2. Okay? And we want to find the left Riemann sum, which means that on every interval, we take the left point. So on the first interval, you take the left point. On the second interval, between those 2 points, you take the left one, then the left one, then the left one. And just judging by the picture, this looks like we're going to get a terrible estimate. That's okay, right? Terrible estimates hopefully lead, and they will lead, to amazing estimates, which is what we want. Love to teach a course in horrible estimates, and that's as far as you get. At the end of the course, you'll have a bunch of answers that are not quite right.
I need to
For sure.
put your hand up if you're in my grade 12 online phys ed class.
So then, when we find the heights of each of those rectangles, we just plug in that left point. So when I plug in 0, I get -3. When I plug in 1, I get -2. When I plug in 2, I get 1. And I plug in 4, I get 13. I add up all those rectangles. So in this example, maybe you don't even have to write that down. All those FUX. Yeah. Going to add up all those rectangles, we're going to get 23. Get a good estimate? Probably not. Is it the best you could do? No. Just do the exhaustion thing. You could just make more rectangles and get better and better and better. So, left Riemann sums. Use the left endpoints to find the heights. Depending on the intervals they give you, you can find the width of those intervals quite easily from the width that, right? Can you see that this one's 1 wide, 1 wide, 2 wide, 2 wide?
Can you quickly go back?
I can quickly go back. Want me to uncover? Not a bad estimate at all. The actual answer, 54. And it wasn't very much. Again, the new method, that method we're going to get to is almost as quick, if not quicker, than even this with only, what did we do? Only 4 rectangles. This is using the concept of an infinite amount of rectangles, and it's way faster. Okay. All right. Try this next one on your own. Do A with the left, do B with the right, do C with the midpoint. See what answers you get, check with your neighbor. You want to write everything out. If you're doing the left Riemann sum, your left endpoints are 0, 0.5, 1, and 1.5. Each of them has a width of a half. So you could factor, I factored the 1/2 out in front here. So I could just add up. This height is 2, this height is 2.25, this height is 2, this height is 1.25. If you can do it for the left side, you can do it for the middle, you can do it for the right hand side. Okay? What do these questions have going for them? They're tedious, right? And they're annoying. That's those positives we can take out of this so far. So, right, there's the right-hand side ones. I'll just, if you want to write it down, I don't know if it's even worth. I think the picture is probably helpful. Imagining where the right endpoints are. Notice how now we're using the dots on the right-hand side. Just judging by the picture, definitely looks like an underestimate for the area. When we look at our first one definitely looked like an overestimate. And it's not necessarily that the left or the right or the midpoint one's always the best. So far it looks like the midpoint ones have been winning, but that's not necessarily the case. Can I move down to the midpoint one? So now we're using the midpoints. 3.375. Are we curious what the actual answer is? So we're going from 0 to 2. What was our function? X squared, x plus 1 squared minus, oh man, I have to scroll, sorry, quickly scroll to the top. Negative x squared plus x plus 2. I love it when there's a 0. Because the one you have to subtract where you plug in the 0, the mental math is nice and easy. If I plug in the 2, I'm going to get negative 8 over 3 plus 4 over 2 is 2 plus 4. 6, which is 18 over 3 minus 2 over 3. 10 over 3 or 3.3 repeated. The midpoint one is it the closest? Again, we don't know the shortcut yet. We're not paying any attention when I show you that. All's good. Everybody good? We've got a table here. The AP exam loves using tables because they can check if you understand what the idea is based on the fact that you're given nothing to work with other than a bunch of numbers. So they tell us that the function f is continuous on the closed interval from 0 to 12 and has the following values. They want you to use the midpoint Riemann sums with 4 subintervals of equal length and figure out, given this data, what's the area under the curve if these were the only points you knew. Can't even see the graph. And you're supposed to try to figure out the area under the curve and estimate it. 4 subintervals of equal length. How wide is each interval? 3. Okay? They're going to go from 0 to 3, 3 to 6, 6 to 9, and 9 to 12. They'll each be of width 3. This chart would give you enough information to find left Riemann sums, right Riemann sums, and the midpoint Riemann sums. If you want the midpoint Riemann sums, you're going to need to use the 1.5, the 4.5, the 7.5, and the 10.5. What I'm circling now in red are the heights of your 4 rectangles. Does that make sense? Those are the heights of our 4 rectangles. The width of our 4 rectangles are all 3. So I take those numbers that I circled, here I'll scroll up just a little bit so you can still see them, right? 3 times 1.45, 3 times 5.05, 3 times 12.25, and 3 times 23.05. Mathematically, if you factor out the 3, it might make your math quicker to do. You could quickly type these numbers into your calculator, add them up, then times by 3, and we get 125.4.